Welcome to G Fun Facts Online. In the deep stillness of a tropical night, an extraordinary predator hangs upside down from a silken trapeze, motionless and virtually invisible. This is the net-casting spider, a member of the family Deinopidae, commonly known by a slightly more intimidating title, the ogre-faced spider. With its long, twig-like body and exceptional camouflage, it blends seamlessly into the rainforest understory, looking like nothing more than a broken stick caught in the leaves. But when darkness falls, this arachnid abandons its disguise to deploy one of the most astonishing hunting strategies in the entire animal kingdom. Instead of doing what most people expect spiders to do, which is weaving a passive, stationary web and patiently waiting for victims to blunder into it, the net-casting spider takes a radically different approach. It actively weaves a rectangular net of highly specialized silk, holds it precisely between its four front legs, and hurls it over unsuspecting prey with explosive, unimaginable speed. While the spider's predatory acrobatics are undeniably a marvel of biomechanics, the true star of this nocturnal spectacle is the silk itself. For decades, material scientists, chemists, and structural engineers have sought to understand exactly how spider silk achieves its legendary balance of strength, elasticity, and toughness. However, the silk of the Deinopidae pushes the boundaries of material science even further than we ever thought possible. Recent discoveries regarding its nanoscale architecture, its incredible dry adhesive properties, and its intricate shock-absorbing mechanics have ignited a massive surge of interest in the field of biomimicry. By decoding the mechanical secrets of the net-casting spider, engineers are currently unlocking an entirely new era of advanced materials, ranging from revolutionary wound dressings and dynamic body armor to robotic space debris catchers. But to truly understand the immense mechanical demands placed upon this highly specific Deinopidae silk, we first have to understand the spider's extreme lifestyle. Net-casting spiders are obligate nocturnal hunters. This means they operate exclusively in the dark. They detect their prey, which ranges from walking insects like crickets wandering the forest floor, to flying targets like moths, navigating the understory, through an incredibly sophisticated combination of acute hearing and unparalleled vision. Their visual system is an absolute evolutionary masterpiece, dominated by their posterior median eyes. These are the largest simple eyes among all arthropods on Earth. Facing completely forward to maximize light capture, these colossal eyes give the spider its characteristic ogre-like appearance, and they are up to 2,000 times more sensitive to light than human photoreceptors. In fact, they are significantly more efficient at gathering ambient light than the eyes of owls, cats, or even diurnal jumping spiders. This extreme sensitivity allows them to track the precise, rapid movements of prey in near-total darkness, locking onto a target when a human wouldn't even be able to see their own hand in front of their face. Once a target is locked in, the spider executes its strike, and this is where the biomechanics become truly mind-bending. Hanging from a non-sticky frame web via a thick dragline, gripped securely by its hind legs, the spider suspends itself directly over a thoroughfare, essentially acting as an organic trapdoor, waiting to spring. It uses its first two pairs of legs to stretch the rectangular capture net it has prepared. Depending on the exact location and trajectory of the prey, the spider will either lunge downward to pin a walking insect to the bark or leaf litter, or it will execute what scientists call a backward strike, to literally snatch a flying insect right out of the air. During this violent, sudden kinetic event, the spider expands the area of the silken net up to 10 times its resting size in a fraction of a second. The prey is violently entangled, and the spider immediately begins to bite and wrap it. Now, pause and think about the physics of what just happened. For a physical material to survive being stretched to 10 times its original resting size in a mere fraction of a second, while simultaneously absorbing the immense kinetic energy of a struggling, heavily armored insect, it requires an architectural blueprint that defies all of our conventional human engineering trade-offs between strength and elasticity. Usually, in human engineering, if you make something very stretchy, it breaks easily. If you make it very strong, it becomes brittle and shatters under sudden impact. The net-casting spider laughs at these limitations. And the secret begins with the fact that its net doesn't use glue. If you walk outside and touch the web of a common garden spider, you will immediately feel a sticky, wet residue. Those spiders are what biologists call acribolate, meaning they rely on microscopic droplets of a viscous liquid glue to ensnare their prey. The net-casting spider, however, belongs to an ancient, specialized lineage of cribbolate spiders. These spiders manufacture a completely dry, glue-free capture silk. The secret to this astonishing dry adhesion lies completely at the nanoscale. Net-casting spiders possess a highly specialized spinning organ called the cribellum, which is a flattened plate located just anterior to their spinnerets. The cribellum is essentially a microscopic showerhead, covered in thousands upon thousands of microscopic spigots. From these tiny spigots, the spider extrudes thousands of ultra-fine nanofibrils. To give you a sense of scale, some of these fibrils measure an unimaginably thin 10 to 30 nanometers in diameter. That is thousands of times thinner than a human hair. It is thinner than any synthetic fiber currently produced by human manufacturing, and yet it is capable of extreme, localized extensibility. To process this massive, chaotic bundle of nanofibrils, the spider uses another highly specialized tool, a comb-like structure on the metatarsus of its fourth pair of legs, known scientifically as the calamistrum. As the raw silk is extruded from the cribellum, the calamistrum vigorously brushes it, teasing the tiny fibrils into a tangled, incredibly dense, wool-like structure. But if there is no glue, how exactly does the net ensnare prey so securely that a thrashing insect cannot escape? The answer takes us completely out of biology and directly into the realm of quantum physics. The adhesion is powered by van der Waals forces. When the incredibly dense, fluffy network of nanofibrils comes into physical contact with the surface of an insect, temporary fluctuations in the distribution of electrons create instantaneous dipole moments at the atomic level. These temporary dipoles instantly induce opposite dipoles in the atoms of the insect's own exoskeleton. Because the total surface area of the millions of tiny, combed fibrils is so astronomically high, these relatively weak atomic attractions multiply across the contact area into an overwhelming, unbreakable adhesive force. But the spider doesn't just rely on quantum mechanics. It also leverages fluid dynamics in the form of capillary forces. The surface of most insects is heavily coated in microscopic layers of protective cuticular waxes to prevent them from drying out. When the net-casting spider's net strikes, the insanely dense nanopores of the cribbolate silk act exactly like a sponge, rapidly absorbing the insect's own protective wax. It literally turns the prey's biological defenses against it to permanently seal the bond. Because this incredible dry adhesion relies entirely on nanoscale proximity to work, it is extremely sensitive to the surrounding environment. Detailed studies have shown that when cribbolate silk is exposed to high moisture, the water causes the highly textured, combed puffs of nanofibrils to collapse in on themselves. This instantly reduces the surface area, drastically dropping the stress forces and strain displacements, essentially switching off the van der Waals adhesion. The fact that these spiders can somehow tune and adapt their dry silks to function effectively in incredibly humid tropical rainforest environments is yet another biological feature that is currently driving intense scientific inquiry. But creating a net that is sticky at the quantum level is only half the battle. The net must also possess the raw structural integrity to withstand explosive stretching and the violent thrashing of heavy prey. Deinopidae captures silk is not a monolithic material. It is not just one kind of thread. It is a highly engineered composite material consisting of up to 8 distinct silk types. The structural framework relies on highly extensible pseudo-flagelliform core fibers. These are then bound tightly together by paracribbolate connective fibers, and finally swathed in that dense, dry cloud of cribbollar adhesive nanofibrils we just talked about. For years, materials scientists operated under a fundamental paradox. As I mentioned earlier, in synthetic materials, high elasticity usually comes at the ultimate cost of tensile strength, while strong materials tend to be hopelessly brittle. But in 2026, researchers analyzing the silk of the rufous net-casting spider, scientifically known as Asianopus subrufa, uncovered exactly how nature bypassed this limitation. Using incredibly advanced scanning electron microscopy, researchers discovered a brilliant, jaw-dropping dual-component design. The core of the thread is made of a highly elastic speedroin protein fiber. But surrounding this elastic core is a completely secondary system of tightly coiled and looped silk strands, extruded from an entirely different set of the spider's silk glands. When the spider lunges in the dark, and the web is suddenly subjected to massive kinetic force, the elastic core does not immediately take the strain. Instead, the coiled loops enveloping the core begin to gradually straighten out. This progressive unspooling acts as a highly sophisticated mechanical shock-absorbing system. It bleeds off the destructive kinetic energy of the impact, dissipating the force over critical milliseconds, and preventing the core from snapping prematurely. Only once these structural loops are fully straightened out does the inner, highly elastic core fiber finally begin to stretch to its maximum capacity to secure the catch. This incredible level of customization is a pure testament to millions of years of evolutionary biological engineering. By separating the load-bearing and energy-absorbing components into entirely distinct biological pathways, the spider weaves a composite fiber that vastly outperforms any single material synthetic equivalent we have ever created. The revelation of the net casting spider's structural and chemical mechanics has essentially opened up highly lucrative, world-changing avenues in the field of biomimetics. Biomimetics is the design and production of materials, structures, and systems modeled directly on biological entities and processes. By meticulously replicating the exact mechanics of Deinopidae silk, researchers are now actively developing disruptive technologies across multiple massive industries. Let's start with next-generation adhesives and biomedicine. The dry adhesion capabilities of cribellate silk offer a perfect blueprint for creating incredibly strong, completely glue-free adhesives. Traditional chemical glues degrade over time, they leave sticky residues, they fail in extreme temperatures, and they can be highly toxic or irritating to human tissue. By replicating the 10 to 30 nanometer fibril structure of the net casting spider's web, engineers are currently developing synthetic dry adhesives powered entirely by van der Waals forces. In the field of biomedicine, this could lead to absolutely revolutionary wound dressings and surgical tapes. Imagine a bandage mimicking cribellate silk that could grip fragile human skin securely without requiring any chemical adhesives that trigger allergic reactions or rip away healing tissue upon removal. Furthermore, because the van der Waals adhesion of these specific nanoscale structures naturally weakens when wetted, such bandages could be brilliantly designed to securely hold a deep wound closed when dry, but then release painlessly and instantly when exposed to a very specific medical solvent or sterile water. Moving beyond the medical field, we look at extreme shock absorption and protective gear. The discovery of that coiled loop shock-absorbing system in the silk of Asianopus subrufa is currently reshaping structural engineering and protective textiles worldwide. Imagine synthetic bionic fibers woven into modern body armor or Kevlar vests. Currently, Kevlar stops bullets through sheer, brutal tensile strength. It catches the bullet, but the immense blunt force trauma is still directly transferred to the wearer, which can easily shatter ribs or cause severe internal bleeding. By engineering synthetic cables with a highly elastic core perfectly surrounded by coiled, unspooling loops just like the spider silk, researchers are conceptualizing next-generation armor that can incrementally absorb and dissipate the kinetic energy of a ballistic impact before ever relying on the core's final tensile strength. This same biomimetic principle is also being vigorously explored for deep space aerospace applications. Engineers are looking at lightweight shielding for satellites designed to gracefully absorb the high-speed impact of micrometeorites, and for automotive crash structures designed to dissipate the terrifying energy of high-speed collisions smoothly, saving countless human lives. Then, we have the thrilling world of bionic robotics and aerial capture systems. The net casting spider is quite literally inspiring the future of automated defense and robotics. One of the absolute greatest challenges in modern global security and aerospace is how to safely neutralize non-cooperative flying objects. Think of rogue unmanned aerial vehicles, or UAVs, trespassing in heavily restricted airspace around airports or military bases, or the growing hazard of hypervelocity space debris orbiting the Earth. Taking direct inspiration from the predatory behavior of the Deinopidae, elite engineers have developed bionic robotic capturing systems. Utilizing highly advanced optical tracking devices that directly mimic the extreme motion sensitivity and low light gathering power of the spider's massive posterior median eyes, these automated drone interceptors dynamically track fast-moving targets. But instead of using hard capture claws or mechanical arms that might shatter, break, or violently deflect off the target, causing more debris, the interceptor deploys a flexible, highly elastic net known as a tethered space net robot, or TSNR. It entangles the rogue drone or space debris securely and softly. The highly adaptive algorithms powering the deployment of these nets are deeply, mathematically informed by the precise forward and backward strike mechanics of the ogre-faced spider, ensuring that the net completely closes and avoids catastrophic mechanical failure during a high-speed kinetic capture event. Next, we have to look at advanced nanofiber manufacturing. While the spider's web is a profound marvel, the physical tools it uses to weave it are equally revolutionary. When human engineers attempt to manufacture synthetic nanofibers using an industrial process called electrospinning, the incredibly sticky, static-charged fibers frequently adhere to the manufacturing machinery itself, clogging extrusion nozzles, halting production, and costing companies millions in downtime. To solve this maddening industrial problem, researchers turned their electron microscopes onto the spider's calamistrum, that microscopic comb on its back leg used to manipulate the highly sticky nanoscale threads. They discovered that the calamistrum isn't just a simple comb. It features a highly specialized microscopic ripple and teeth-like structure that fundamentally prevents the sticky nanofibers from adhering to the spider's own legs. By meticulously engineering synthetic, biomimetic combs with these exact anti-adhesive microscopic ripples, manufacturing facilities are now finally able to seamlessly manipulate, comb, and weave synthetic nanofibers at an industrial scale without catastrophic sticking or clumping. Finally, there is the massive frontier of smart wearables and chromogenic textiles. With the exponential rise in wearable technologies, there is a massive global push to replace petrochemical-derived synthetic fabrics with smart, highly sustainable materials. Spider Silk Biomimetics is completely leading the charge in developing futuristic fabrics that actively adapt to environmental stimuli. By deeply analyzing exactly how spider silk perfectly blends hydrophobic or water-repelling and hydrophilic or water-attracting properties to survive in fluctuating humid rainforest environments, chemical engineers are looking to weave synthetic silk-like microfibers into smart celluloses. These incredible adaptive fabrics could physically alter their thermal insulation and moisture-wicking properties on the fly based entirely on the wearer's real-time body heat and sweat output. Furthermore, analyzing the intricate crystalline structures of various silks has shown that their specific, nanoscale surface textures interact with ambient light to produce breathtaking structural colors without any need for toxic chemical dyes. In the very near future, chromogenic fabrics utilizing these microscale biomimetic weave structures could provide vibrant, completely fade-proof clothing that effectively reduces the massive, global environmental footprint of the highly polluting textile dyeing industry. But all of this incredible biomimicry brings us to a crucial bottleneck: the genomic frontier. While we can closely observe, study, and mechanically mimic these structural designs, producing genuine synthetic spider silk at a massive commercial scale remains a truly formidable scientific challenge. Spider silk fibers are composed of highly complex, incredibly repetitive structural proteins called spidroins. Because spiders are inherently cannibalistic, highly territorial predators, they cannot be farmed in massive facilities like placid silkworms. If you put 10,000 spiders in a room, you eventually end up with one very fat spider. Consequently, the scientific focus has completely shifted to the genetic level. Recent, groundbreaking advances in arachnid genomics have prioritized the total DNA sequencing of the Deinopidae genomes. By meticulously isolating the exact genetic sequences that code for the highly extensible pseudoflagelliform core and the separate genes that code for the thousands of cribellar nanofibrils, scientists are working around the clock to genetically engineer common bacteria, yeast, and even agricultural plants to mass-produce these miraculous spidroin proteins inside massive industrial bioreactors. We are essentially teaching yeast how to brew spider silk instead of beer. In conclusion, the net-casting spider is a profound, undeniable testament to the boundless, breathtaking ingenuity of natural selection. In its simple, relentless quest to secure its next meal in the pitch-dark understory of a tropical rainforest, this unassuming, stick-like arachnid evolved a dynamic hunting mechanism and a complex architectural material that effortlessly outperforms centuries of human engineering and materials science. From its massive, light-devouring posterior median eyes to the microscopic quantum-level van der Waals interactions of its dry adhesive silk, absolutely every single aspect of the Deinopidae is perfectly optimized for dynamic, explosive energy management and absolute predatory efficiency. As human material science finally begins to catch up to millions of years of biology, the biomimetic applications of the ogre-faced spider's incredible silk are set to fundamentally revolutionize our modern world. In the delicate, incredibly tangled fibers of a dark rainforest web, we are literally finding the blueprints for indestructible bionic armor, life-saving, pain-free medical devices, and robotic sentinels guarding our skies and low Earth orbit. Nature has already conducted millions of years of rigorous, unforgiving research and development. Humanity simply needs to cast a wider net, look closer at the world around us, and learn to read the extraordinary results.